here, density. It turns out everything, no matter what kind of stuff you use, obeys this rule. If it's hot and not very dense, it's a gas. If it's cold and dense, it's a solid. There's sort of an intermediate region, which is a liquid. And in this temperature density diagram, there's a large region which is forbidden. Can't go in there. Why? It's forbidden. And you notice there's no units here. Why are there no units here? Because this applies to most everything. The exact units on the labels will depend on whether you're talking about iron or helium or what have you. So suppose, for instance, this is a plot for water. Suppose we looked at this x here corresponds to, imagine this is 20 or 390 or 290 Kelvin, 20 degrees Celsius, and 0.1 of its natural density. You can't actually have water in that region. And you might say, well, who's to stop it? This is 0.1 grams per centimeter, that's 10% of regular density. Why can't I just take a liter jar and put 100 cc of water in it, so it's 10% full, have it at room temperature, screw the top on the jar, and then shake it like crazy and make water in the forbidden zone? What do you say about that? Well, as soon as you stop shaking it, the water all falls to the bottom of the jar, where the density is 1 gram per centimeter. So at the bottom of the jar, you've got water over here. At the top of the jar, you've got water vapor, which is also the same temperature but much lower density. You don't have nowhere in the jar do you have any of this stuff in the forbidden region. Why am I telling you about this? Because it turns out that Bose-Einstein condensation happens at these forbidden temperatures. Everywhere where BEC happens, it doesn't matter what material you use, you're down in this forbidden zone unless you go to such very, very high density that it solidifies. And a solid doesn't count for Bose-Einstein condensation. Once you have a solid is like the enemy of BEC, because to make BEC, you need to not be able to tell the one atoms from another. Some of you may have seen these beautiful images using scanning tunneling microscopes where they take images of a crystal lattice of individual atoms. You can see the individual atoms in these beautiful rows and columns. That's what a solid is about, where the atoms are frozen in place, and you can tell one atom from another, not because they're different, but because they've got different addresses, different sites where they can't move from. So once you've got a solid, a crystal like that, you can't have BEC. So BEC is forbidden. Can't do it. Short talk. Thanks for coming. Unless we do it, and this is the theological insight I wanted to get to. Well, how can you possibly do it if it's forbidden? But once the most key thing you learn in theology is that the things that are truly impossible, they don't bother to forbid. Good point. Also, let's take it a little further in theology. They also don't bother to forbid things unless at some level they're kind of fun. Right? I don't recall ever reading a commandment against bashing my head against a brick wall, because I don't want to do it anyway. So the fact that this is forbidden should be kind of encouraging at some level. I mean, okay, I'm not making a big comedy out of it, and that is mostly just a play on words. This idea of sort of a forbidden stuff, to chemists, this is an idea we think of as metastability or supersaturation. It's possible to take a gas and cool it slowly down into this forbidden region and not have it turn into a liquid or a solid, but just stay in this forbidden condition, a supersaturated gas, a metastable gas. It's why when a jet flies overhead, you see a cloud growing behind it. It's because right before the jet passed, there was a supersaturated gas there, and it gets stirred up by the jet and it condenses. As long as you don't let the fluid, as long as you don't stir it up too much, as long as you don't let it touch the walls of the chamber you're keeping it in, I'll tell you how to do that. You can cool a gas. In our case, this is a log plot here. We go down 20 orders of magnitude down in this region where at a temperature where it really ought to be a solid, but we keep it as a gas just long enough for it to form a Bose-Einstein condensation for us to do. So we're kind of playing a trick on Mother Nature. There's a little bit of history. Sure enough, there's Satyendranath Bose. I visited his home city of Calcutta a couple of years ago. Einstein came up with this idea a long time ago. It was thought it was impossible to get that cold. In the early 80s, people using the dilution refrigerators, sort of classic traditional low temperature physics techniques, tried it mostly with hydrogen. There was groups in Amsterdam, MIT, University of British Columbia, Cornell, using spin polarized hydrogen dilution refrigerator. This was long before I got into this racket. So people have been trying to make Bose condensation for at least a decade before I got into it. But this technology called laser cooling came along and jump-started things. Laser cooling was invented by several people, but very prominent among them is Bill Phillips, who's a guy up at University, well, he's at partly at Gaithersburg and partly at University of Maryland. basically, the idea of laser cooling is, you think of a little bit counterintuitive. You think usually lasers make things hot. In factories, they use lasers to cut out the leather or the soles of shoes and what have you. We're using lasers to make things cold. Basically, the photons hit an atom. All the photons carry not only energy, but a little bit of momentum, and the photons bounce off the atom and push the atom around. And using the force, basically, from that, you can slow an atom down. If you go out into the bright sunshine and stand there and the sun hits you on the chest, yes, it warms your chest a little bit, but it also pushes you backward. Step backward, staggering in the sunshine. And you might think, of course, I've never had the experience of staggering with the force of a beam of light. Why is that? You're probably thinking it's because photons are too small. But that's not it at all, and I mean this in the kindest possible way. The real problem is all of you are too big. And if you were a reasonable size, like the thing that I'd like to study, like atoms, you'd find the force of a photon bouncing off you no laughing matter. A rubidium atom, which is scattering photons at the maximum rate, undergoes an acceleration of about 10,000 times the acceleration of gravity. So you can really push them around hard. And in our case, we bring in laser beams from the north, south, east, west, up and down. They intersect here, and they push the atoms into a little ball. And I don't have time to talk about this. But also, it wasn't my idea. We just stole it from Bill Phillips et al. You can actually use it for slowing the atoms down and cooling them off. It was not an idea that we invented, but I'm not a proud man. In particular, I'm not too proud to steal a good idea when I see it. So we did that and got very cold. But it turned out it wasn't cold enough. Carl Wyman and I, working together, realized it was not cold enough to get to Bose-Einstein condensation. We went way, way down. We needed another technique of cooling. And that technique was called magnetic trapping. These days, basically we make a bowl, and I've drawn it here as if it's like a big translucent blue bowl, but really it's a magnetic field. Way out here we've got coils of wire, out here, up, down, side to side, coils of wire. We run current through it, it makes a magnetic field. All these atoms we know how far up the side of the bowl they can roll. And we know the shape of that bowl, and it's a parabola. So if it goes, however far it goes up there, we take the square of that and multiply it by that curvature, and we get the energy. So here's a cloud. I showed this slide for, I scanned it from one of my original acetate slides. I showed it for sort of sentimental reasons. It used to be that memory was expensive. And we would only save like parts of our images because we took lots and lots of images. So back of discs and RAM, it's all as expensive. So this thing should look kind of like a football. We look at kind of the full width half maximum of that cloud. It's about 2 millimeters across. We know the shape here that works out to 20 microkelvin. After we've done some evaporation, instead of being 2 millimeters across, it's only 0.2 millimeters across. You take the square of that, so the ratio should be a factor of 100, 20 microkelvin, 2 microkelvin, 200 nanokelvin. That's how we get the temperatures of these things. And the densities we get from seeing like how dark the shadow is. This is a negative image where it looks white, that's where it's dark, the shadow is dark. So that's the kind of thing we do for measuring temperatures and densities. All the measurements we do in these clouds, we take this way. And in truth, even this kind of measurement is too harsh. The fact that the cloud of atoms has to absorb a few photons out of our laser beam to cast a shadow, that already heats them up. So the act of taking their picture destroys the condensate. So if we want to see how the condensate evolves over time, we have to make a condensate, measure it, which kills it, and make a new one, and let it sit there a little longer, measure it, make a new one, let it sit there a little bit longer yet. Stick these images together, kind of like claymation, make a little movie of what the condensate's doing. Each image is from a new condensate. Okay, so this was so far I've come up to right about say early months of 1995, when I had finished being a postdoc, which was in 1992. I went around looking for a faculty job, and I told people, hire me to be your assistant professor, give me some money to start up a lab, I'm going to make Bose-Einstein condensation. And they didn't believe me. In particular, people had already been trying to do Bose condensation for more than a decade. They said, yeah, right, kid. We'll show you the pile of papers written by people who couldn't make it work that way. So I wasn't getting a lot of traction with